Hey, mathletes. What we're going to look at in this lesson is we're going to start talking about something known as derivatives. Okay, what the heck is a derivative? Well, you didn't even know it, but in the last unit, in a lot of the limits questions, you were actually finding the derivative. So whenever you were using one of our two formulae, so this one here, or this one here, what you are actually doing was finding something called the derivative. And so we write it as this little f, and then that little tick there, we say prime. So we'd say f prime at a. So what the heck was a derivative or is a derivative? What we're doing is we're finding the slope of a tangent to a curve. That's also the same thing as the instantaneous rate of change. So that's why we're doing these things. Now, what we're going to do in this lesson is we're just going to play around a little bit more with our two formulae here. But then what you'll learn in the rest of the unit, because some of these questions are like, oh, they take so long to do. They definitely take a long time to do. But what we'll figure out here is we're going to have an easier, quicker way after today's lesson. Okay, but for now, we're going to stick with our basics. So the first one says for f at x is equal to 2x squared minus 4x minus 1, determine f prime at 4. So that's the derivative at 4. What that means is we're finding the slope at 4 or the instantaneous rate of change when x is 4. Okay, I want you to keep that in mind. Okay, now it's up to us which one of these two formulae we use, okay? Doesn't matter. But what'll end up happening is you will start to develop a bit of intuition as to which you prefer to do, right? Like you'll get better at one than the other, okay? So I'm going to use first principles, which is the first one, because generally that's the one I prefer. So A is 4, that's A right there. But sometimes what will happen is, even though I prefer first principles, friends, is that as I start doing the work, I'm going to go, oh, this is awful. Maybe I should have used the other method, Newton's method. Okay, but we'll see as we go along. So now remember what we did when we were finding these limits last unit, right? Is we sub everything in. So 4 plus h for x, minus 1, and then minus f at 4. Okay, so we've still got to find f at 4. Well, f at 4, I need to sub into that function as well. So there's a lot of little calculations here, and you can see why people would make some mistakes, right? Because there's a lot, and you know, I'm sure I'll make a mistake even right now. Okay, so you just got to take it slow. Okay, just start simplifying. So 4 plus h squared is 16 plus 8h plus h squared minus 16 minus 4h minus 1 minus, and then inside my brackets here, what do I got? 32 minus 16 minus 1 over h. Like, this is just a big beast. And I want you thinking that. I actually want you saying to yourself, oh, really? Like, do I have to keep doing this? Yeah, I actually want you saying that to yourself, because there has to be a better way, and that's the next lesson. Okay, let's keep simplifying. So I'm going to multiply in the 2 and change the order at the same time, because I like my lead to be that. Okay, minus 16 minus 4h minus 1 minus, what do we get here? 32 minus 16 is 16 minus 1 is 15 over h. Now remember, our goal here is we need that h in the denominator to divide out, don't we? So we're going to find out if I've made any mistakes right in a second, right? Okay, 16h minus 4h is 12h. And then 32 minus 16 minus 1 minus 15 is 32. That's 0. Okay, right there from last unit, I know I've done this correctly, because now those h's can divide out. So now I've got 2h plus 12. And after all of that work, I sub in 0 and I get 12. Okay, what a pain in the butt that was. guess what? You'll be able to do that question in about 30 seconds after the next lesson. Now, what does it mean? What this means is there's two different ways. There's more than two ways, but the two that we normally analyze in Math 31 is we would say this is the slope of the tangent. The slope of the tangent is 12 when x equals 4. Or the other easy thing to say is the instantaneous rate of change, or I'm just going to say rate, when x is 4 is 12. Now, what is this? In a few questions later on, we're going to talk about time. Maybe this is 12 meters per second. Okay, so I want you to think that when you're finding the derivative, you're finding the slope of the tangent line, which is the same thing as saying we're finding the instantaneous rate of change. Okay, so what we just did was the same question we did in the last unit, just with what we're calling now a derivative. Okay, so here's g at x. Let's find the derivative of this thing. Okay, so the derivative of this thing, again, I can use either formula I want. Okay, and let's find, I don't know, g prime at, what's going to make numbers easy here? 5. Okay, let's find g prime at 5. So what I'm going to do on this one is I'm going to do the other method. So I'm going to say g prime at x is equal to the limit as x approaches a of g at x minus g at a over x minus a. Okay, so this is what's known as the Newtonian method. Okay, so we want g prime at 5. So we want the limit as x approaches 5 of g at x, so 2x minus 1, minus g at 5, well, g at 5, so that's 2 times 5 minus 1 over x minus 5, just like that. And we start simplifying. So again, make sure you're writing limit all the way down the page. 2x minus 1. Okay, that's going to be the square root of 9, which is 3. And then now we've got a problem. We have division by 0 if we try direct substitution. So now what we do is we multiply by the conjugate. All right, do you remember doing this? We rationalize the numerator. You were told some lies in earlier grades that you always rationalize the denominator. That was a lie. A complete lie. Go back and tell your teachers they were liars. Okay, and then remember, do not distribute the denominator. Leave it just like that. Okay, in the numerator, because they're conjugates, I simply have to just multiply the first term and the last term like that. And simplify. And I'm running out of room because these questions take so much space. This is 2x minus 10 over x minus 5 square root of 2x plus 1 plus 2x minus 1 plus 3. But now do you notice what we can do? I'm going to factor out a 2 here. And look at that. Boom. There's our problem gone. Now we can do direct substitution. And we're going to get the square root of 9 is 3 plus 3. I'm completely out of room. 2/6. So what we just found was the derivative of g at 5 is 2/6, or hey, let's simplify that down, hey, 1/3. There it is. That's the slope of the tangent line when x is 5, just like that. Okay, last thing we got to talk about here is in the first unit, we talked about whether a limit existed. And so we'd analyze from the left and the right. We're going to do the same thing here with derivatives. Does the derivative exist? So that's what this means. Differentiable. What that is asking is does this derivative exist? So for a derivative to exist, that means the derivative on the left and the right of the function has to be the same. Okay, it's easier to show it graphically. So here is the absolute value of x. Okay, the derivative doesn't exist here because it doesn't exist at 0. Here's how I know. I want you to think of the derivative as the slope of the tangent line. Well, the slope of the tangent line. Well, I can see over here on the left and on the right, the slopes of those two things are going to end up being very, very different. We'll talk about that in a second. But here's the other thing. Look at 0. How many different tangent lines could I actually draw? I could draw an infinite amount. So the derivative does not exist at this sharp cusp, or if I had a hole in my graph, any discontinuity. So the derivative does not exist as soon as graphically, if I have a cusp or a discontinuity. Okay, that's how we can see it visually. So if I had a point of discontinuity or something, it's not differentiable. Okay, algebraically is a touch trickier, but it's not bad. Okay, remember when we have the absolute value, this is actually a piecewise function. This is x is greater than, or it's positive x if x is greater than or equal to 0. That's the right-hand side of that graph over there. And it's negative x if x is less than 0. That's the left-hand side of this graph over here. Get rid of all those tangent lines. So there's what that function is. Well, guess what? Let's take the derivative of this thing. Well, what I'm going to tell you here is the derivative of these two things, the derivative on the left, the slope of the tangent line, and the derivative on the right. Well, friends, you don't even have to do your derivative rule we just did. On the right, that's a straight line with a slope of 1. The derivative is the slope of the tangent line. The derivative of that is 1. On the left, the derivative is the slope of the tangent line. So guess what? The slope of that tangent line is -1. So what we say is the derivative from the left is not the same as the derivative from the right. The derivative does not exist at 0. So look what I'm going to do. On my restrictions, I am going to remove the equal to 0 because the derivative does not exist at that sharp point. Okay, so very much like something we did in limits, talking about does the limit exist from the left and from the right. Okay, we'll explore this idea of differentiability more as we go through the unit. But for now, friends, in this first unit, you're going to do some more work with limits. And what I want you to think as you're doing it, here's the 2 different ways we calculate a limit. So the things we were working with last unit. And what I want you to think is this is awful. How am I ever going to get anything done? Because this isn't even that complicated of a function. And it still took me 5 minutes to do. There has to be a better way. And guess what? There sure is. Okay, so the better way's coming. But until then, do some more limits. See you next time, friends.